But everybody sympathizes.
Good evening. We have all gentlemen here. In this evening, we are going to hold a public lecture. This is about 3D printed metal superalloys by Professor Harsha K. Chellaya. On behalf of Mechanical Engineering Sectional Committee and ISL, we would like to welcome you all. We have prominent gentlemen participating to this lecture, starting from Professor Pallavatta, President of IESL. We welcome you, sir. And we got to know about Professor Chellaya through Dr. Kamal Lakshe. We welcome you, sir. And this Professor Chellaya is a batchmate of Engineer Palitha Vikramasekara. We welcome in this evening you. I went through Professor Chellaya's profile. It's a world leading and prominent profile. He's a professor of mechanical and aerospace engineering at University of Virginia, USA. But I am going through his profile and I found out he's a graduate from University of Nuwaraeliya. He's a prominent and brilliant student at the university and he conquered the world. These days, especially with the politics, we are talking about developing this country. There are a lot of debates, arguments, and a lot of things are spoken. We always look for foreign expertise. We are searching everywhere, but if somebody come here, you can see Professor Harsha Chellaya. He's one of the prominent academic and the prominent engineer in the world. If I introduce Professor Harsha Chellaya, he is a professor of mechanical and aerospace engineering at University of Virginia, USA. He got his PhD from mechanical and aerospace engineering from Princeton University, USA. He's a graduate from University of Moratuwa. He got a first class honors. He is a fellow of American Society of Mechanical Engineers and associate fellow of American Institute of Aeronautics and Astronauts. He is a visiting fellow of Peterhouse College, Cambridge University, UK. He is a board member of Journal of Combustion Theory and Modeling. Currently he is on 2 years assignment at National Science Foundation USA as a Director of Combustion and Fire Systems. With this introduction, I would like to invite Professor Harsha Shellaya on stage to deliver your presentation.
Yeah, thank you. Thanks for your kind introduction, and thanks for being here. And so I've been at University of Virginia since '92, about 27 years, and it's located about 100 miles from Washington DC. So if you're in the neighborhood, please contact me. I'd be happy to show you the place. So Parita happened to visit Washington DC about last March, and we had a good time. He visited my lab and had a great interaction. So a few words about the university. A university was built by the third president of the US, Thomas Jefferson, and so he likes to be remembered not for being the president of the United States, nor the architect of the Constitution. If you go to his gravestone, he says he's more remembered for building the university. So university was completed in 1819, one of the first public universities in the country. Of course, Harvard and Yale is much older, but one of the oldest public university. This is the image of the university. So the idea was, it's called academic village. Original university had 10 faculty houses. These are faculty houses, and in between was student dormitories. So students and faculty lived together, and the lectures were held in this big building called Rotunda. So there are 3 levels. The top level is the library, ballroom, dancing hall, and other levels have the lecture rooms. Okay. Of course, now it has expanded a lot more. So now the current population student body is about 25,000 students. But I think at the beginning, probably there must have been a couple of hundred students. Okay? So it's a pretty nice old historic building. But today I'm here to talk about some my research work, and also with the idea of introducing some new manufacturing concepts and how you could use this concept to application in Sri Lanka. So that's my take-home message for you. So I want to break down my presentation to 3 major themes. So my research is on gas turbine or jet engine research, as well as there's another class of engines called Ramjet, Scramjet engines for aero vehicles that can travel at Mach 5 and above. So I'll say my first third of the presentation, I'll talk about my own research a little bit to get you oriented with that. And in this research, we are using this new manufacturing process called 3D printing. I mean, you may have heard this. Plastic 3D printing is standard now, and now these are metal 3D printing. This is very high temperature alloy, nickel chromium alloy, which can withstand very high temperature and stresses. So many gas turbine engine components are made out of this material, and so these can be printed with 3D machines now. Okay? So I want to introduce you some of the challenges and how you could use this technology in modern research as well as for application in Sri Lanka. So yeah, last part is essentially, 12 years back I was interested in using, Tranak, I didn't see you. About 12 years back I was interested in using gasified biomass for power generation and heating purposes in TA factories as well as garment industry. But at that time, we had a technical problem with one of the gas turbine I was going to use. And my hope is that with 3D printing, we can solve those issues. Okay, so I'm hoping that with this manufacturing, we can apply this, go back and pursue this combined heat and power concept for application in Sri Lanka. Okay, so that's the 3 themes I want to share with you today. And if you get it, it's great. And so hope that you take home message. Okay, so my talk Propulsion is as my research. Metal superalloys is an area that of interest to many applications, and I'm interested in power for application in Sri Lanka. Okay, it's essentially CO2 neutral, using biomass, generate heat and power. So this is an image. It's not very clear. This part in our flow field, if there's no water cooling, this material can withstand 1200 degrees Kelvin. Okay? And it's a high temperature material. But with water cooling, we can. But if you in this configuration, if you start combustion, this material can survive. So the back of this essentially, we have cooling water going into this system. There are 5 cooling channels inside this, and that's the only way this can survive at high temperatures. Okay. So, and this cannot be manufactured with traditional machining technique. Only through 3D printing that you can have this intricate internal details. Okay. So, let me give a brief background the difference between gas turbine and Ramjet, Scramjet engines. Okay. So, in Sri Lanka generally we refer to jet engines, which is same as gas turbine engines, as opposed to that propeller-driven engines, right? So, typical big aircrafts typically fly at Mach 0.85 conditions at flight altitude about 40,000 feet. That corresponds to about 660 miles per hour or 900 kilometers per hour, right? So, typical engines fly at that velocity, and most of the, so this is our illustration of gas turbine engine. In the gas turbine engine, you have 3 major components. You have a compressor, which pressurizes your intake gas to about, Rolls-Royce 1000 operate about 50 atmospheric pressure. So you pressurize through a series of turbine and rotor blades to about 50 atmospheric pressure. Then you bring the fuel in and burn in the combustor, and then you have a series of turbine blades. These first 3 set of turbine blades gets exposed to very high temperature. Only this material, Inconel, was invented in 1940s by there's a engineer called Frank Whittle. He was the inventor of the gas turbine engine in UK. There was an equivalent in a person in Germany, and this Inconel was designed to operate the gas turbine engine at high temperature. Okay, so there are different class of Inconel material. This is Inconel 718, which has slightly different composition of nickel, chromium, and iron in it. Okay, so these first 3 blades are the most critical blades because they get exposed to very high temperature, currently about 1300 C centigrade, but these turbine blades are internally cooled with compressed air, and then also this material typically are coated with what you call thermal barrier coatings, right? So that's how these engines now operate very high efficiency. They are pushing 50-55% efficiency, thermal efficiency. Okay. Next generation, they want to replace this with ceramics. With ceramics, they're hoping to go up to 1700 C, and with 1700 C, they're expecting to go to much higher efficiency, 65%. Okay. So there are issues. So this 3D printing, although it has rapidly, the plastic 3D printing is very common. In the US, almost all high schools have plastic 3D printers. People have in their homes as well. But metal 3D printing is taken off only last, I would say 8-7 years. It's rapidly increasing its applications. So some components are being built, but aircraft engines are still testing because structural strength is of issue. So they don't want engines to fail in, even at high altitude, right? So they are slowly introducing small components. The SpaceX, the rocket company, Elon Musk, is using 3D printed components very aggressively. So there are certain industries they are pushing this technology, but aircraft industry is very cautious because safety is paramount, right? So they are slowly using them. So if you go to like Rolls-Royce has manufacturing plants in Sheffield and Bristol, and they have 3D manufacturing facilities, and they use this heavily. So so much for the gas turbine engines. My research is mostly funded by Department of Defense. I have some funding from Rolls-Royce looking at emissions, not the emissions from the combustor. But my major research is from Department of Defense, US. We are looking at these Ramjet, Scramjet engines, vehicles flying at Mach 5 kind of a velocity. So essentially 5 times this velocity, right? We're talking about 3,000 miles per hour kind of a velocity, okay, or higher. And so the main difference between the Ramjet and the gas turbine is that in the Ramjet there is no rotating parts. At high speed, you can take the airflow, we can slow it down, and you can pressurize to high pressure. Okay, not very high, not 50 atmospheric like this, but still to decent pressure. And then you mix the air and the fuel, and you generate high temperature, high pressure gas to generate the thrust that you need. Okay, so in fact, this idea was first proposed in 1910, before this gas turbine engine was developed in 1940. But to date, there's no really working ramjet engine. There are a lot of experimental engines, and so of course US and Russia and China are trying to develop scramjet engines. There are a lot of issues, mostly related to materials, and at a high velocity, we have very little time to mix your fuel and air mixture. So generating, mixing, and combustion is very challenging. So those are the issues that we are researching in our lab at University of Virginia. Okay, so the main point I will take away is that there are 2 classes of engines, typically for subsonic cases, Mach 0.85, and then these are more research type cases. Okay, and then of course rockets. So rockets technically can take off from 0 to whatever velocity, but main difference is that rocket engines, at least current versions of it, you have to carry your fuel and the oxidizer. So you pay a penalty by needing to carry the oxidizer with you. Whereas these engines are what you call air breathing, you have to carry only the fuel, right? So your weight of oxidizer is reduced by going to this Ram and Scramjet engines. So my next chart is to how do you compare these 2 different systems, right? So if you want to look at the performance of the 2 different systems, so this is a way to compare the 2 complete different systems. So I'm sure you have taken dynamics, what is impulse, right? Force time time, and specific impulse is essentially thrust divided by the mass flow rate. So the units of, you look at the units of this, the specific impulse units of seconds. So if you take a gas turbine engine, typically has a specific impulse about 6,000, right? So these are GE, I think CFM56 engine are the large engines. So Rolls-Royce strength 900 or 1,000, all they are below Mach 1. So they have a specific impulse roughly about 6,000, very high specific impulse. And as you go to high and high velocity, your specific impulse goes down. So this is for the Concorde. Concorde flew at about Mach 2 to 2 times the speed of sound, has a specific impulse about 3,000, which implies that its efficiency is not very high, right? That's why eventually they shut it down, because it is expensive to operate. Okay. Now, if you want to go to high and high velocity, like Ramjet, which is like Mach 3.5 to 5, your specific impulse goes down, right? And if you want to go to Mach 5 or 6, then in terms of fuel consumption is a very, very bad design. But for military purposes, they don't care of the efficiency. They want to have a fast flying missile, right? So, but even there though, if you compare the rockets have specific impulse of less than, I don't know, maybe 500, right? But so if you want to have a missile going at say Mach 7, Scramjet engine is better than a rocket, because in the rocket you have to carry your oxidizer. The Scramjet engine, if you can make one working, you can essentially increase the payload by having high specific impulse. So this is why China, Russia, US working very hard to get this engine working, so that you can have a. So one problem with the rocket intercontinental missiles, you cannot once you launch it, you cannot really control it. Whereas if a hypersonic engine with the wings, you can maneuver it, so you can avoid your enemy. You cannot shoot it down easily. You can avoid it. So that's why the biggest advantage of the scramjet hypersonic vehicles. You can avoid enemy radar and try to attack somebody else. But I'm not interested in military application. I'm interested in civilian application. So originally, these engines were, NASA was interested in getting hypersonic engine working for civilian applications. Okay, so these are, still NASA is interested in, but currently the research is being dominated by the military because that's where the money is. And why hypersonic would be great is, if you think of some long flights. I flew from San Francisco to Singapore, right? It's a 16-hour flight, right? Imagine if you can fly at Mach 7 or Mach 6, can fly in about 3 hours from San Francisco to Singapore, And so, that's personal interest. It won't happen during my lifetime, maybe during your lifetime, one day, it might work. But there are a lot of challenges though, So anyway, there is military application, there is civilian application, and hopefully one day we can overcome the challenges and have fast airlines. Now I should say that although fuel efficiency is very poor, since your flight time is lower, the total fuel consumption is less. So this is why rockets, you want to have maximum chemical energy, get out of the gravitational field, right? So there are advantages of going faster, although your fuel efficiency is very poor. Okay. Now, both these applications, hypersonics and gas turbine, require, increasing the efficiency requires better materials. So materials we are living in a material world, really, So if you have better materials like this, with better coatings, we can run at high efficiency, high performance, right? So material development can have broader impact, not only just propulsion, like I want to talk about this gasified biomass applications for garment industry and tea industry can have benefit from this technology. Okay, that's the take-home message. So don't worry about our research in the US, but there are applications in Sri Lanka with new material and the manufacturing methods. You can have broad impact to humanity. Okay, so that's the take-home message. So few words about hypersonic propulsion. There are many challenges, but at the University of Virginia, we are focusing on thermal management, essentially cooling technology and fueling technology for these hypersonic engines. So this is illustration of a cartoon of a future hypersonic civilian vehicle, right? So this can be, there's a combustion here. This is an illustration, your fuel, so air comes into this, and this is a sort of cartoon of this. You take your air in at say Mach 6, Mach 5, you inject your fuel, then you burn it, you generate a high temperature, high pressure flow and generate thrust. But in this part, the combustor part, the temperature is so high, you have to have active cooling, right? So one idea in this system is to, so in these vehicles, you cannot carry water. All the research is done using water as a coolant. But when you're flying this, you cannot carry water because it adds weight to the vehicle. But one concept is use the fuel itself to cool this high temperature region. So our plan is currently we are using water to cool this. The next step is to use fuel, feed the fuel through these cooling channels and cool this hot surface, and then take the fuel will undergo pyrolysis and then take the cracked fuel and feed into the combustor. Okay? So this is the next step that we are going to follow. Okay? So, so you cool this with the fuel and then inject the fuel upstream and then burn it and generate the thrust. Okay? So the facility we have at University of Virginia, we can mimic a plane flying at Mach 5. So at Mach 5, if you bring the air molecules, what you call stationary conditions, your temperature goes to what you call stagnation temperature. The stagnation temperature is about 1200 Kelvin. So if you want to test a plane going at Mach 5 on ground, one way to do that, heat the air up to 1200 degrees Kelvin. So we have a giant heater about 30 feet deep going into the ground, and we can heat air up to 1200 Kelvin, and then we have this test section here. This is where Palitha saw in our lab. So here we have this, maybe this is better. We have this test sections with windows. We can essentially mount this part inside this. So this is this part here. So looking at somewhere like that, air is coming from left side, and so fuel is fed upstream, and we can anchor this flame over this and generate thrust behind this. Okay, so the challenge here is to make this part cool, and also the velocity of this flow varies from 400 to 1000 meters per second. So you have a less than millisecond time to burn this fuel air mixture, right? So typically, if you don't have the right conditions, it gets blown away, and then you don't have thrust. So the question is, how do you keep it anchored there and burn steadily? So we can run this facility typically 5 hours continuously. So each time this part gets exposed to 5-6 hours of high temperature experimental conditions, and it survives based on cooling techniques we have. Okay, so we are doing a lot of testing in this lab, especially at Mach 5 conditions, and then we work with Air Force Research Lab and NASA on this, and currently with the Navy, US Navy, and we can. The other thing is that with the 3D printing, we can also change the geometry very quickly and easily. So this part cost me about $5,000. In the US scheme of $5,000 is not bad, and typically this experiment we get about $400,000 funding for a year. So $5,000 is not that bad. So we can, but with the 3D printing, we can change the geometry and test different conditions to understand the flow dynamics in here. And then we also have a simulation group, does computational simulation of the flow field. And then we also have a diagnostic group that do a lot of advanced laser-based diagnostics to quantify velocity, temperature, measure temperature, molecules non-intrusive in laser-based technique. So those research is ongoing in the lab. Okay, so this is a high-speed image of looking at the. So you can see this. This is the essential emissions from the flame at 50 kilohertz frequency. You can see the flow dynamics taking place in this system. Okay, the flame is anchored in this cavity region. Okay, let me not dwell too much on this. So this is sort of an illustration of the sort of cross section of the flow path. So we have a giant tank in here, 30 feet long. This is of course tilted. Then we have a nozzle. We can introduce flow at Mach 2, and then we inject the fuel upstream in here, and this is the test section over here. Okay? And we do all the testing in this part here. And this is sort of a CAD drawing of this part, and this part is built in 3 components. And so and the cooling is a critical part of this part, and I'll talk about that. So the thermal management is a challenge, right? As I mentioned, the 3D printing essentially saved us. If you have to manufacture the normal techniques, we'll have to make this in 2 parts and then fuse it together, and it gets complicated. Okay, so with 3D printing we can do very intricate designs of that. So let me talk about that. Let me skip all these things in here. So this is an illustration, I mean the photo of this part without fueling, and so I think there's a so here is a case where our first version of this failed. So our first version, we didn't have enough cooling, and when you inject the fuel and air into the system, when the combustion started, it completely blew up. Okay, so cooling is very critical, and also 3D printing technique is very critical. Okay, and this is the image of the fail part. So we failed twice before we got to the final version. So let me talk about the event that took us to successful design. First, as I mentioned, plastic 3D printing is very standard. In fact, first we printed a piece like this plastic and tested out without combustion. Okay, and the metal 3D printing, as I said, has really grown exponentially, and so these machines now, mostly German. There are a couple of companies called EOS and Concepts, and the smallest one, like about foot by foot footprint, I think it's about $250,000. It's not too bad. So essentially, it's a box, and the way you do this is, so you have a CAD drawing, and you use so depending on the material you want. In this case, Inconel, we take 40 micron, roughly 40 micron powder, and you layer a powder, and then the laser head will go and melt it, selectively melt it where you want it to be fused. What you call right? And so people are also experimenting electron beam method as well. Now the resolution depends on the laser, what you call focus beam, right? So I was told the smallest feature you can print currently is about 100 to 200 microns. So I have printed a part with 150 micron orifice that can be printed with this Inconel material. Okay. Now there's one problem though. If you have a cooling channel inside a big block, when you try to if you start from the bottom, right, you have cooling channel. So you can, for bottom part is very easy to print by layer by layer. When you come to the top, you have essentially have a ceiling, right, hood, and typically the particles can melt and fall down and form stalactite. And if those form, then after you finish printing, you can get the powder out. So that's what happened to us first time. When you try to print this, we tried to, like typical mechanical engineers, we thought we could have a round cooling channels in this part and cool the part portions, and that failed. So this part is essentially a shell. It's a 1.25 millimeter thick shell, and inside is hollow, right? And then other thing is that this is printed at an angle, 45 degrees. So you print, start from one and you go layer by layer, and so you had to design. So you had the 3D printer. You cannot just go and print anything that you want. You have to think a little bit about this layer by layer, how they form. And so typically, if you have got a circular channel, instead of circular channel, you have to print what you call teardrop shape. The top has to be 45 degrees. Okay. If you try to build a circular top, it usually fails. So you have to, your CAD design, you have to put thought has to go into it, how you are going to print this. Okay. So these companies, have a lot of experience, they can print this. So this is another example of 3D printed part. I got it from internet, and you can see these intricate channels, and of course this could be machined and fused together, but 3D printing, you can print all these little details in one shot, right? And part like this can be printed straight up, right? The other thing is that when you're 3D printing in these machines, when you have a big box, you don't print only one part. They will pack as many parts as possible. So you do 10-15 jobs in one given time. So that's why this cost me $5,000. If I had to print one single one at a time, it may cost a lot more money. The powder itself costs about $10,000 for a huge fill an entire box. But if they print 15-20 parts, then your cost goes down. Okay? So anyway, so this technology is there, and also another thing to notice that the surface is rough. The roughness is essentially this 40 micron kind of surface. You can though, if you need so in fact we have another part I printed, which we have machined is using EDM, electrical discharge machining, and with that, like here, you can get smooth surfaces. So you can post-process these things and get smooth surfaces as needed. Okay. So the what do you call the type of architecture that you can design and build with these real metals, humongous. Applications are enormous. So I think Sri Lanka should definitely take advantage of this. So far, I have not found out anybody using these printers here, I think it's something that we need to encourage industry in Sri Lanka, I think. Okay, so the part, this is the internal drawing of this part. It's not, so in fact we printed in 3 parts, 3 modular pieces. So this is the base, the support material, which is very simple. They have intensive cooling, but this is the critical part. So we printed, designed this like that we can change this geometry as needed, right? And so in this part we have 5 cooling channels coming from the bottom up. So there's a 1 cooling channel here, another in here, and the most critical part is this part here, and then the downstream here. So inside this there are 5 cooling channels, and this is very thin wall, 1.25 millimeter thick shell essentially. And by doing that, we are able to take the powder out, and we get all the flow rate that we needed. Okay. All right. So that's all I have to say about the technology. And so here is a sort of image. So I think there's a video cartoon here. This actual running of experiments. So we are fueling, in this case, ethylene as a fuel, and we can stabilize the flow, the different fueling amounts. This is equivalence ratio about 0.43. You know about chemistry, equivalence ratio, right? Lean conditions. This is a lean condition. You can see less intensity. This is due to we have a gasket on our between the glass and the material. Our gasket is glowing in here. Okay. So this works. We can run. This has seen about 100 hours our test run, and you don't see any burn marks on this. Okay. So because of intense cooling in this system. All right. Let me take this and try to combine this manufacturing and gas turbine to application in Sri Lanka, which you may be of. I'm personally interested in this. As I said, about 12 years back, I was passionate about this, and I had technical issues. And then I got busy with other research. I didn't have time to go back into this. I think time is probably right. If anybody's interested, we can talk about this later. So my idea is essentially in Sri Lanka there are plenty of biomass, and I've been to a friend's tea factory, and they use firewood for just heating. Very primitive way of heating drying tea leaves. So idea was that can you gasify this biomass and then use it cleanly, generate power. So this is combined heating and power, CHP. Some of you may have heard about this, right? So not a new concept. In fact, University of Virginia had a combined heating and power system in 1917, I think. They discontinued when from direct electricity to AC electricity. So in around 10s they discontinued that. So it's not a new concept. So this is a tea factory down south towards Avisavala side, and around this factory it's full of firewood, right? And the way they use is essentially they have a wood-fired furnace, right? And there's a heat exchanger, and the air goes over tea leaves, and you dry air at 500 degrees Kelvin kind of temperature, right? So the analogy of this is, to me, is that if you have, say, a reservoir on a mountain, right, water reservoir, and if you have a paddy fields in the valley, what do? You can always open a gate and send the water to the paddy fields and irrigate your farms, right? And so you're using high water head to irrigate your paddy fields on the valley. To me, that's a waste of water head, right? Potential energy. Similarly, firewood has essentially chemical energy, potential energy. So as molecules have potential energy, right? And if you want, when you burn the firewood, you create a temperature about 2000 degrees Kelvin, right? Typically flame has a temperature 2000 degrees Kelvin. But you're taking that high temperature gas, you're bringing down temperature to 500 Kelvin to dry tea leaves. So you're using all that potential energy, okay, chemical potential energy. So idea is that if you have a water reservoir, what you do is you have a hydropower generator, you generate electricity, and you still have enough water head to irrigate your paddy fields, right? So similarly, this biofuel has enough chemical potential energy, you can derive power out of it, and excess heat can be used to dry tea leaves at 500 degrees Kelvin. Okay? So that's the whole concept of combined heat and power. Just like using water for intelligently, you know. So this is to me primitive way of using biomass to dry tea leaves, right? And so better way would be to use what we call biomass gasifier. And in a biomass gasifier, what you do is you heat the fuel, like a fluidized bed to about 1000 degrees Kelvin, and you mix it with water and you generate what you call synthetic gas. Syn gas is essentially a mixture of carbon monoxide, hydrogen, and then you have carbon dioxide and nitrogen. So you can use this syn gas mixture to run a boiler. That's what's done in this tea factory. Or you can take this syn gas and run a gas turbine and generate power, and still you have excess heat to dry your tea leaves or heat, heat buildings. So this is 12 years back, and this is this year. I was at Nuwaraeliya at this tea factory. I was talking to the guy at the front desk. I asked, what you do is your raw material, what you call all the twigs from the tea factory. He said, well, they are using gasified biomass. So I said, can I talk to your engineer, right? So he took me back. This one is essentially their heating plant in the back. And so this is an Indian, I think company in Gujarat. They make this gasified biomass system. But this tea factory is purely depending on biomass. So they buy biomass, essentially the fast-growing firewood, and they partially oxidize this, and then they feed this to the boiler, the dual diesel biomass burning boiler, and then they heat. This is a hot water tank, and this hotel, its water is essentially all derived from biomass, and then in the winter they use drying as well, except they don't use the biomass to generate power, right? That's why I call this a better system. Better approach is a bit cleaner in a sense. You can take when you gasify biomass, you have a lot of junk, so you can separate that out. Whereas here, it's very sooty, very unhealthy sort of way of burning it, right? So this is working, and we're running this all the time. So I was pretty excited. I thought I should share this with you guys. And so this is they take this from here, go to this next building, and this is a supply of syn gas and fed into the boiler. Okay. So my challenge to you is to take this biomass and connect it to a gas turbine and generate power, and you still have enough leftover heat that you can you provide hot water and heating for a building or a garment industry as well. Okay, so they have sort of a promo of the system. They do a CO. Don't ask me too many questions. They claim that they save about 136,000 rupees a month, I think, by going from diesel to biomass, and they claim that net CO2 saving about 5,760 probably, I don't know, kilograms. Okay, so that's how they are advertising. But it's and they use these what you call fast growing epil, and this is something this forgot the name of it. This cinnamon as a biomass source, right? And those are the things that was this in bags in here. And so they're not cutting fresh wood to fire this. Essentially, they're using these fast growing trees to generate the biomass needed. And so question is, can you do better than this, right? So do better is my idea that I was hoping to pursue before. So I have two micro turbines. These are small scale turbines, can generate 30 kilowatts each, and they generate about so they have you can buy system 30 kilowatts, 65 kilowatts, or 200 kilowatts, but you can stack them in parallel, and you can develop up to 10 megawatts if you want to. Okay, and each one will generate about 30 to 200 kilowatts. But the problem is that individually the electrical power generation, they are only about 29% efficient. So they are very inefficient gas turbines. So they are only good if you want excess heat, like tea estates, garment industry. So if you want to just use the fuel to get power, this is a very bad idea. The reason is that these turbines operate at a very low pressure ratio about 5. Remember I talked about civil aviation engines, they operate at pressure of about 50. So that's how they operate at a very high thermal efficiency. So by operating at lower efficiency, they are not ideal for just for pure power. But if you need a heat source, like tea estates, garment industry is a perfect solution. Okay? So idea is that if you can gasify biomass into CO, hydrogen and methane, then we can use this system. But the problem is, when I was exploring this idea 10 years back, when you gasify biomass, you get about 18% hydrogen. Now, hydrogen is a very fast burning fuel, right? And these turbines, the way the fuel injectors are designed, could not handle high hydrogen content. So, which means it required modification of the injector. And that time, I didn't know about 3D printing, and there was, reverse engineering was not easy. Okay. Now with the 3D printing, I think we can easily reverse engineer these injectors and take any biomass and design this gas turbine to run at any conditions. Okay. So this is in this cabinet, the gas turbine is pretty small. It's about that, maybe about 1.5 foot long, about foot in diameter. A lot of insulation around that, and there are 3 injectors. Okay. So essentially it's a single shaft. It spins about 95,000 RPM, and it has what you call centrifugal compressor and a centrifugal turbine. It's a very very kind of simplistic design, but it is essentially meant to run at low efficiency but combined heat and power conditions. So these injectors are the problem, right? It could not handle high hydrogen content. And the reason being that this injector, this is a cross section of the injector, which I got much later by going to the patents. I found the patent of the company, and I found the design of this. So these injectors, essentially, you take the compressed air, and your fuel comes from here, and there are holes on the side, and it's designed for an ideal fuel air mixture, and the flame sits sort of lifted from this tube. If you send a lot of hydrogen, what happens is that this combustion region gets sucked into the injector. And doesn't matter what material it is, without cooling it is going to melt down. Okay? So what it requires is that if the fuel composition change, you need to go and change the geometry of this injector, and then you can adjust its velocity or the cross section diameter to account for the high hydrogen content fast burning fuel. Okay? So I can easily pull out this injector from the turbine I have, and then with the 3D printing we can redesign this and able to run any fuel air mixture. Okay. So again, I brought this in here. You can 3D printing, you can design. Building this is very simple. After doing this is pretty trivial, I think, in my opinion, building an injector like this. Okay, with Inconel material, which is probably better than the materials that's in here. Okay, right? So I think this is my last slide. The take-home message to you is that with novel, I call this a game-changing technology. Once this technology is there, we cannot go backwards. It's like GPS, right? And old days we used to travel around with maps, and who uses maps anymore, right? The GPS is, it's like a game-changing technology. 3D printing, I think, in my opinion, in the next 10 years is going to be a game-changing technology. You can reverse engineer anything you want. You guys especially are good at CAD drawings. Once you draw it, you can easily, chip it to these machines and you can print it out. You got to pay attention to the details of orientation and all that, but can be done. Okay. So I'm hoping to retire in about 3-4 years. My passion is to go back to this and make this work. Okay, so so I'm interested in finding partners here. Anybody with clever ideas interested to pursue this will be especially application in Sri Lanka. Yeah, summary. So additive manufacturing with super alloys. I mean, as I said, you can make this with titanium, different materials. I mean, copper considered hard. In fact, copper can be done as well now. Okay, so people are exporting. So Inconel 17, there are different class of Inconel. This is 718. There's Inconel 625. Different class of Inconel material can be used. Application in Sri Lanka, I think clearly the tea industry, garment industry, where the heavy heating is needed, I think definitely can benefit from this technology, right? And as I mentioned, the 3D printers, the prices are probably coming down. I'm sure Chinese are getting into this. I mean, Japanese have their own machines, and Chinese are starting to build these machines. I'm sure the price will come down, and the price of the powder is the most expensive eventually. The laser heads are should not be that expensive. Yeah, so with implementation of combined heat and power, with biomass available in Sri Lanka, I think certain industries can benefit. Now, in terms of emissions, I'm a combustion guy, and I think long transportation, we should all go electric. Okay. And my cars are all hybrid and plug-in hybrids, but civil aviation, planes carrying heavy batteries it's not a good choice. Okay, especially large planes. So there are certain applications hydrocarbons have benefit, right? Sri Lanka should really go after wind energy and solar for sure, because we have tremendous wind energy sources here, and we should down transportation definitely go towards hybrid, electric plug-in electric type vehicles. But certain applications, when you need heating, the US, if you have a hybrid car in the winter, if you need heating, it's a bad idea, because if you think about it, you get electricity and you want to convert electricity to thermal energy, it's very inefficient, right? So you'd rather have a hydrocarbon fuel vehicle, because excess energy, the radiator, you get so much energy, you can heat the compartment, right, passenger compartment. So you have to be careful where you launch hybrid electric vehicles in the north, in the very cold regions. I think it's a bad idea. So my wife drives a car in the winter. We are only 4 miles from home to the work, and essentially she drives cold, because by the time get to work, the engine part doesn't warm up enough. So if you use electricity to convert to heat, is a very inefficient method. So there are applications where battery, hybrid technology is great, but not all applications. Okay, so you have to, at the end, it's going to be a balance of between wind, nuclear, thermal, solar, and hydrocarbons, and will essentially save us from the global warming issues. Okay, so that's all I have. I'm happy to go into depth if you want to, and happy to chat with you about any other questions you may have. Thank you. Yeah.
Thank you, Professor Chellaiah. I think this is a presentation with a lot of information, a lot of cutting edge and very advanced stuff, and I hope there may be a lot of questions. We would like to open this forum to questions, and Professor Chellaiah will answer the questions.
No questions. Yes.
We can open the thank you very much, Professor. I think very especially because this area is kind of unknown to Sri Lankans, and it's your kind of like one hour of doing things there. So, and they were very proud that Sri Lankan is doing research there. Maybe I ask a good question. I usually ask one or two. Now you mentioned about this powder. How is the powder? How does it come? Now the traditional 3D, it's kind of a resin, kind of a polymer.
Right.
So it's like a big pot, like a report is doing the thing. But in this case,
Yeah.
it is for propulsion, the propulsion units.
No. Yeah. Okay.
Which needs to be, kind of solid, so in one go, can it make, especially the powder. How will powder come? It's a kind of a oxygen,
It's a dry powder. It's a dry raw Inconel 718 powder. So I'm not. By the way, I'm not a material scientist, right? I'm a mechanical aerospace engineer. So first disclaimer, right? So, but in these machines, they come in dry powder. It's an inert bath in an inert environment, and so you pack the chamber. From what I understand, I've seen from a distance, not really type the powder myself. So if you fill the chamber with this powder, you don't fill it completely. So you first one layer, and then the laser will go and melt it. It's called selective laser melting, SLM. That's the standard, So sintering kind of a process. It's a sintering essentially. And then once it's done, one layer, we apply another coating of 40 micron, I don't know exactly what the powder is 40 micron, I don't know exactly the thickness of the layer, maybe it could be 100 microns. They put a layer of powder, and then laser will go and again selectively heat based on your design. So build layer by layer, so essentially you're sintering it, right? So on issues that sometimes they have porosity, so structural issues, So,
of course, you can have can be effective.
Right.
So especially on these turbines. Now,
Exactly.
especially when they take the turbines,
Right.
properly angled,
Yeah.
working at very high temperature, associated cooling rates as well.
Yes, exactly.
So it is not properly done.
Yes,
So,
absolutely, yeah. So this is, as I said, this is why aircraft industry is very cautious about it. They don't want the blade to break off. So there are a lot of research going on. They're printing. I've been to Sheffield, Rolls-Royce manufacturing plant. They built all these things, but they are still doing a lot of testing on structural, strength at high temperature conditions. So we are doing testing. So turbine blades, even though we make out of the metal, you apply what you call environmental barrier coatings. There are many layers, and so they are in fact testing the survivability, called life cycle set testing of these coatings and structural. So they exposed to cyclic pressures, cyclic temperatures. So they are doing a lot of testing before they really launch them into actual flying machines. They already have problems. Like Trent 1000, Rolls-Royce took about 7 billion hit. They have issues with some of the components. So they are not going to just go into 3D printing and use those components without extensive testing. So the issue is the structural integrity, the porosity. So this is why the laser. So they are testing electron beam melting instead of laser melting. So we can focus it better and try to make sure that no pore structures are there. So for us, this part doesn't see. We have done stress analysis of this, or finite element analysis, because this doesn't see too many forces, so it's not a big issue. So we, in fact, first thing we did was print one like this out of plastic, and in the flow field, 1,000 meters, we tested out of plastic, it survived that, and so we were not concerned with the metal part here. Of course, this got exposed to high temperature, but valid point that it's an ongoing research topic.
Maybe you can do experiments with that, and later take a more out of it and go to traditional for large scale manufacturing. This is excellent for prototypes.
Sure.
Because you don't need otherwise to take a unit like this in traditional days, it could cost you, I suppose, more.
Yeah.
Time to cost from 3D machine.
Right. So
Because if it fails, again you have to take more.
Right.
More productions.
yeah, that's the whole point. So once they are comfortable with the manufacturing technology, they could have 100 of these machines. Each printer can print 10 parts, and so I don't know. Typically take about to go through the entire layer, depending on the size, can take a day or two. And so, it can, scaling up is very easy. That's what I'm saying. The technology is expanding exponentially. I think within the next 10 years, I think it come to maturity and it will become standard, like old-fashioned, lathe machining techniques, So, yeah, CNC machines, I mean, right? So, potential is enormous. Yes, probably.
We have engineering. Yeah.
So another question, maybe touching on your last point, Professor for the significant. Yeah, just taking you to the history. Somewhere around 2000, Dr. he formed a company.
Right.
And target was make use of biomass
Right.
and for power generation. Of
Right.
course, initially there was possibility targeting the industry for CHP. Technology was Indian gasifier,
Right.
but fortunately or unfortunately, the Chinese gas engine,
Huh?
Chinese gas engine reciprocating.
Oh, reciprocating engine. Yeah, right.
Yeah, so initial was 35 kilowatt electricity.
Okay.
With the fuel was the downdraft gasifier with Nuwaraeliya. I think some descriptions will show.
Right.
Gasification was fine.
Oh, it's not easy.
Yeah, not easy.
Yeah, not
But,
easy,
we managed to,
Yeah.
the company managed to,
Yeah.
I was also
Yeah.
part of
Right,
the
right.
managed to do the prototyping and it was okay. Then it was replicated at different phases. But the gasifier, as you said, gasifier technology could not sustain.
Right.
Well, it was a almost downdraft, not reduction type of thing.
Right.
And probably the cleaning of gas cleaning to suit the gas engine was not correct. So we had a lot of practical difficulties. Ultimately, over
Yeah.
4-5 years,
Right.
it was managed to sell few gasifiers, the large
Right.
one to one of the ceramic industries as well,
Okay.
for thermal investigation
Right.
for their furnaces. But ultimately it died off.
Right.
But the issue was probably we could not get the proper gasifier
Right.
to suit our fuel sizes and requirements.
Right.
So it is probably, and then following up with that, currently there's a gasifier keep working at Monaco, mechanical gasifier. They also did some testing, getting the gas engine successful.
Yeah.
But your idea, taking it to the next level, probably, yeah, we can plan subsequently or maybe through email we can.
Yeah, definitely.
And it's good to see that we get feedback between industries for us again. And so it's that because there would have been a long period because of bad experience.
Right.
In the gasifier.
Right.
Not with the technology.
Yeah.
But we can.
So,
And then I think
right.
your dream of
Yeah.
revisiting and revitalizing this
Yeah.
would not be that difficult, I guess.
I don't underestimate, it's not easy. So, have you been to IISc, Bangalore? So, Professor Mukunda is a famous, so I know him very well. So, he's very passionate about this, and all these historians are the ones who are going to build these gasifiers, So, he essentially, his lab has gasifiers, but they are running reciprocating engines.
Right.
And it's not a very clean operation, and so but I think gas turbine is a better device because reciprocating engines you have to be fueling, it's had to be very, you have to cyclic or adjust it. Whereas gas turbine engine can be a bit more forgiving in terms of fuel injection because it's continuous flow, can take some fluctuations. So in my opinion, gas turbine engine is a better choice for this gasified biomass, right?
Correct.
And so so the gasifier itself is not very easy, but so this design. So there's a guy here in Colombo. I can't remember what got his name now. Now he has left. He's gone to Canada. He had a similar Injector, right? Injector.
Yeah, it was in the company.
Okay, right. Yeah, Cyrus in communication. So he had a very similar size one, right?
Yes.
They bought it from India, you know. Angkor, exactly, right. So, but this one, so this is a tea factory in Nuwaraeliya. They bought this for, the whole thing cost about 7.5 million rupees, right? Only for 10 years. And so I got the engineer's name. I mean, seems to be running very clean. And I mean, it was running while I was there. I was very impressed. And you know, it's much better than what I saw at IISc in India. It's a much dirtier, you know, lab. So this is super clean. I was really taken by this, you know. And if the way these guys have mastered it, and if you can get this gas, I can easily put my microturbine in there and run this. Of course, I had to change the injector. So this is a great opportunity to work with these guys and use their knowledge, and you know, and they're interested in getting the power, because they'll get free power out of it, right? So I think we should definitely go after this. So Capstone, the microturbine is a Capstone microturbine. So they have a rep in India, but not in Sri Lanka. And he was willing to come and meet with me. This is 12 years back. But then, you know, company told me, don't try it, you're going to burn it down. So I never did anything at that time. So, and it's been, and I showed you this, right? Yeah. So it's collecting dust outside, you know. So I need to wait for 2-3 years, retire, and then, you know, follow up on this. I'll be happy to take up your offer. We should work on this. Yeah. This is, I think, exciting. I think things you can do with this, you know.
So in our mind, it was something that we left out. But 20 years back, with that experience,
Yeah, no, you should go and see this. This is in Nuwaraeliya. Tea factory, you know, I'll send you the contact information. I mean, I'm open, I won't share with anybody, you know. I think this is a great, huh? It's a tea factory. That's the name, tea factory at Nuwaraeliya. Yeah. So, I mean, so they essentially, it's a hotel, you know. Yeah, tea factory hotel, right. Yeah.
Excuse me, I have a question regarding that radiating. Do you get any advantage properties like surface hardening and abrasive resistance like that? How
So-
does that compare with the other technologies?
Right. So probably you can, after treat it if you want to, right? You mean annealing kind of technique, annealing effects? Yeah. So there are material scientists who do all those kind of analysis, right? And we have not done that. But there are, so our department, I mean, school has a material science group, and they are essentially testing smaller 3D printed segments and looking at stress analysis. So there are groups working on that. So probably if you want to big components, you'll have to do some post-processing annealing to get the right, you know, strength, you know. Yeah. So I'm not expert on that. Yeah.
It's a essential property of the complete compression resistance for gas turbine engine, the proper brakes and everything.
Right.
So still you have to go to other post processing.
Yeah. So all these companies are doing that. GE, Rolls-Royce, they have invested heavily on this 3D printing, and they are doing extensive, you know, working with universities like Bristol and, you know, Sheffield. They have massive labs. I mean, so they not only after 3D printing, they do X-ray analysis to look at the, you know, porosity and stuff like that. There are a lot of post-processing going into it. Yeah. So in fact, we have not done the X-ray analysis. You can do X-ray analysis and look at the internal geometry. So we are getting the cooling rate we wanted, and it survived. So we are looking at more combustion more than the materials. But so X-ray analysis is very common. Yeah. Yeah.
Can you please explain what are the challenges we face if we use such as typical turbine?
Say it again.
What are the challenges we will face if we use syngas in a typical turbine?
So essentially, if you take a typical fuel air mixture, there's certain combustion properties, like combustion wave goes at certain velocities, right? So syngas, for instance, has, it's not a pure fuel. It has a CO hydrogen, and then of course it has some nitrogen, CO2, and water vapor. So the burning velocity is not same as, let's say, methane, natural methane. So these gas turbines are designed to run the micro turbines I have, right? So this one, it can run on pure methane or natural gas, which is not pure methane, like 93, 97% methane, and also can run on digester gas. So if you take cow dung and if you process it, you can generate what you call digester gas, which has typically about 55% natural gas. So this system can run on that. Essentially, the burning velocity still can handle that. Another one can, if you have a what you call the landfills. Landfill generates natural gas. It's called sour gas. So in fact, this is designed to run on sour gas system. Right? So it can handle many fuels, but not high hydrogen content, because its wave propagation is much faster. It gets sucked into the injector, it can burn it down. So that's what this company, they didn't think about using gasified biomass. They designed for the other fuels, not for gasified biomass, which requires this major injector modification.
Thank you, sir. I was actually part of the team where in 2018 at Mr. Murto we designed a ground drop gasified system.
Okay.
So,
so did you
we
measure
are still doing designs for some.
So did you measure the composition of the gas coming out?
Not really, sir, but we were able to calculate the calorific value, but was not able to go for a proximate analysis.
Right. Right. So I think I had the. So this system requires heating value certain amount. There's a range, but this is a nominal value, right? So it requires that much heating to go into the system so that it can run, generate the energy to run the system. Right? So each machine has its own specs. You can do that. Yeah.
So this turbine which can handle producer gas cannot still the commercial level.
Handle producer gas?
Yeah, syn gas. It's not still the commercial level.
I don't think so. So the one issue is that this company is in California near Irvine, and they have a arrangement with the University of California, Irvine. So they donated one of the turbine to me free of charge. The other one I got, from state of Virginia had one they gave to me. So I got both free. But they were willing to work with me, but they have a non-disclosure agreement with UC Irvine. They were not willing to share with me the injector design, complicated issues. So, and I got frustrated and I just gave up 20 years back. And I got busy with other stuff anyway. So, I mean, technically, I could pull out the injector and, redesign it, and I don't have to deal with the company, So, there are other companies who make this. So, Germany, DLR, Stuttgart, they are investing heavily on this micro turbines. They think that this is going to be a big money maker. So, there are entire units working on developing micro turbines for new applications. So there are others who come up with it. So, and Inconel Rand is another company. They make micro turbines as well. So it's not only one supplier, there are others making these things. Yeah. No more questions? Yes.
Not directly related to it. Currently, USA and UK,
Actually, in US, G, and in UK, the Rolls-Royce are the ones who are manufacturing large engines.
Pratt & Whitney.
Also, but especially for military application, I think G, which are workable.
The power
I
application.
did a lot of place on this, especially because I'm keen on jet engine. And now, what is the issue with Chinese are the properties? I mean, they may produce currently, even though they make planes, the only problem that they have is they cannot develop a proper engine which is workable for long hours.
So just say it again. Who is building the
The Chinese.
Chinese? Yes, yes.
Usually,
Right, right.
US has
Right.
actual models which are working.
Sure, sure.
Sometimes maybe 3,000 hours or 10,000,
Right.
15,000
Sure,
hours
sure.
which are working continuous.
Right.
24 hours 7 days.
Yeah.
But now Chinese are unable to do. They have the main plane, copy plane
Right.
designed from America.
Right.
They expect by the only problem that they have is they cannot put a proper finishing to this.
Right.
Even Russia has the same problem.
Yeah.
But Russia is a little way ahead
Yeah, yeah.
than China.
Right.
China is not behind, how
Right.
they show. But with this technology, they can master some of those things, which is the danger. I mean, it increases the arms race. I mean, that's
Yeah.
a revelation, I know.
Yeah.
I'm happy to do
Yeah,
it.
no, no. I know. I mean, world is getting fatter, right? I mean, information travels. Everybody has the same access to the same information, which is a good thing, right? But civil aviation, if one plane goes down, then right, the business goes down. So reliability is a key. Yeah, exactly. So right. So I think all the Chinese can make it. I mean, these things probably, I don't know, their service after, I don't know, 20,000 hours or whatever,
No, their service time is very short.
Yeah, exactly. So,
Life,
yeah.
but they are not.
Right. I mean, so the cost, right? I mean,
They are not
operating
that-
cost is the key, right? Operating cost is high, then it's not going to last.
These are built in Germany. That's what is developed.
It's a thing that is family business, family industry.
Yeah.
I mean, you don't immediately there is story. How they process are they making the heating sequence and all is a secret.
Right.
Yeah. Like I always say, it's like how to make cow university. I mean, for ingredients, and everyone may even have.
Right.
How they make it is a kind of
Yeah.
Now, that is what they don't have. She and those going to be doing this
Right.
from a long time.
Yeah.
The engines are
Yeah.
nothing to worry about, as you say.
Yeah.
Yeah, actually completely applications.
Yeah. I mean, so Japanese are making, right? Honda is making engines. Honda. Yeah. So I mean, they are still mid-size, and they can easily scale up. Japanese, yeah. Right. So I think it's good.
They are on the side resonance, but
Yeah, yeah.
happens is
Right.
there is already a trade war to check out companies doing because they are coming not being building,
Right.
which is an issue.
Yeah.
And you are for interesting because jet engines and military is a application and rocket.
Right. Yes. Okay. Right. Right. Thank you. Yeah. Thanks for that. Good question, enjoyed it, yeah.
Thank you, Professor Chellaiya. Next, we have a moment of appreciation. I would like to invite Professor T.M. Pallavatta to present a moment of appreciation to our Professor Chellaiya.
Thank you very much for your very
Thank you.
interesting.
Yeah, thank you. Yeah, appreciate this. Okay.
Next, I would like to invite Engineer Kumudu to deliver the vote of thanks.
Good evening. President ISL Professor T.M. Pallavatta, Professor Athalagi, Professor Kamal Lakshita, and Chairman Mechanical Section Engineering Section Committee Engineer Asela, and our most valued invited esteemed guest lecturer Professor Harsha Chellaiya. There are no ladies, only gentlemen. It is my privilege to have been asked to propose a vote of thanks on this occasion. On behalf of the ISL and Mechanical Section Committee, extend every a very hearty vote of thanks to Speaker for your important work and sharing with us the findings and opinions today. we we learned about specific impulse of a rocket and the jet engines and hypersonic propulsion and use of this technology in civil flight systems to reduce current flight times. I think in future we can fly to Australia within 6 hours rather than 12. We learned about current challenges in hypersonic propulsion and the interesting thing, cooling system using fuel as a coolant rather than using the water to reduce the, because it's prohibited in design, the flight designs. And Scramjet and Ramjet engines and the most important area I found is the relevant application for Sri Lanka. I think in future I'm thinking about 5 kilowatt micro turbine in my backyard running from household the waste and other things. It's very interesting. And the big thing, the 80 to 90% overall thermal efficiency of this micro turbine is a very interesting factor. When compared to the reciprocating engines, the normal is less than 30% sometimes, as I know. Anyway, a big thank you to Professor Harsha Kechelaya. We are all inspired by your great lecture. And special thank goes to President Professor T.M. Pallevatta, Dr. Kamal Lakshita, and Professor Athalage. I also extend my thanks to CEO Engineer Neil Abesekar and IL staff for their enormous cooperation in organizing this event. Well, gentlemen, an event like this cannot happen overnight because our members work hard to organize this thing. We have been fortunate enough to backed by very motivated young and enthusiastic team of engineers with Mechanical Engineering Sectional Committee. Thank you to the Mechanical Engineering Sectional Committee. Once again, thank you to Professor Harsha Kechelaya and all participants. And good evening. I think roads are congested during this. Anyway, good evening and thank you again.